Sorry. So here's an example of a closure table. The circuit is only closed. Electricity can only flow if both P and Q, both switches, are closed. So P and Q have to be closed. P and Q is true if they're both true, P and Q both. You draw the table like this, and it shows you all the situations where the network is closed. Okay. Now, in their example of what they want you to do in the excursions, they give you this one that's a little more complicated, and they say, well, okay, here's the symbolic expression, and it's pretty ugly, but you come down and you fill in the table. I'm going to do a simpler one here on the under the document camera in just a minute. Mostly the errors were not with the table. It's tedious, but it looks like mostly you knew what to do with a few mistakes here and there. But I want to do a simple one to show you to make sure you can fill in the table. And I'll do that in just a minute. But what I want to focus on for the moment is this English language part of it. You see, it all boiled down to this blue highlighted column here. You took the part in the square brackets and the part in the parentheses over here, the two main expressions, and the last operation performed in the order of operations was this and right here. And so when you did the final operation, you just got these two ones and everything else was zero. Okay. And so they say in words here, under what conditions will the network be closed? Now they start out with this bulleted list, which is the ugly way to say it. They say, okay, it's closed on row 1 here. So let's see, if P and Q and R, if those all three are closed, then the circuit's closed. So they wrote that down. It's closed whenever P, Q, and R are all three closed. Okay. And then they went down here to this next row where it's closed, and they said, oh, okay, also, if just Q and R are closed, then it's closed. So they have these two bullet points in their list. And I don't know, 3 or 4 students, I think, were pretty good at getting to this point where they had the bulleted list. They were not taking it the one more step. And I want to tell you what that's all about and why it's important and so forth. But first, what is this one more step? See, they boiled it down to this sentence here. The network is closed provided Q is closed and R is closed. Because look at those two bullet points. You see how it turned out P doesn't even matter. If Q and R are both closed, the thing is closed, whichever way P went. So the P doesn't actually matter. So the simplest way to say it would just be the network is closed provided Q is closed and R is closed. Now, the authors of the textbook imagine that you will work that out just by looking at the ones and zeros here and trying to say, okay, what is it that makes them all closed? And I'll say some more about that problem in a minute. But at this point, I think if I were in your position, I'd be worried. I'd be saying, sometimes it's hard to tell how it boils down. And if I think I've got a real simple way of saying it, how do I know if I'm right? Maybe what I said doesn't exactly match the same thing. I mean, here it's pretty clear, you know. Okay, look, whenever Q and R is closed, okay, you know, see, it's this time when Q and R is closed, and this time, those are the only times Q and R are both closed, and that's when the overall circuit's closed. It's pretty easy to tell, okay, I've said it in a real simple way, and it really does match. But I would feel worried if I were in your position. What if the table is a little more complicated? And then the other thing I think I would be wondering about is, and how does that relate to me as a liberal arts major? And what I want you to think about, well, so you guys are the ones who are supposed to be good with words, right? I'm thinking here, when I look at a mess like this expression, I'm thinking of something like the tax code, you know? You pay 30% if this or this and this, okay? Or if this and not this, all right? You get these messy things, or in the law, you know, like the Venn diagrams for like how crimes overlap, you know, and a given behavior might count as more than one crime, but not as another one. You get the Venn diagrams or the logical descriptions of what constitutes a crime. So you'd see it in law or in descriptions of contracts, or in psychology, the Diagnostic and Statistical Manual has got all these descriptions. They're like constellations of human behaviors, you know. So this thing overlaps a lot, so we'll give that a name. And you want to, when you try to express something like that, you want to say it in a simple way. All that mess came down to just, you could say, Q and R. That's it, Q and R, after all that. And so, you know, it is a thing that needs to be done sometimes in the world. I'm not saying you'll do it very much, but that's why it even sort of became a subject. Okay. Now, I'm going to make a simpler truth table for you to show you how to fill in the ones and zeros. And then I'm going to do show another one of these where we make a verbal description based on the just the ones and zeros. And then I'm going to talk about something real cool, because there's a system. Okay. All right, so let me get the document camera. So I can just do a small closure table. Now I got to find my good pen. Okay. Yeah, so somebody was asking me about this one in a private chat. I made an appointment. They're all encouraged to do that, but I say, hey, it's a good example. So I want to make the closure table for this one. So now one thing a lot of you guys are doing is when you write it down at the column headings, you're leaving out the parentheses. And the parentheses really make a big difference. They got to be there. It controls how you proceed, the order that you do things in. So now that I drew my parentheses, now I'm gonna list all the possible PQ combinations that could be. And then I'm going to start making my expression. So on the top row, P is 1, not P is 0, Q is 1. What do I do next? Because of the parentheses, you know, we have an order of operations. It's like in algebra, PEMDAS, parentheses. We don't have any exponents, but parentheses. And then the multiplication is like the and the addition is like the or. So the order of operations, we do the parentheses first, the and then the ands, and then the ors. We go from left to right. So what's next in the order of operations is we got to work out the value of the parentheses. Let me fill in all the numbers for all the rows, and then we'll do that and. And I want to check for questions here. Anybody want to put their hand up? Are we okay on just filling in the letters? Probably yes. Yeah, looks like okay. So now I do that or. So as long as either one of them is true, if one or the other is a 1, it's a 1. Okay, so I filled in the whole parentheses. All right, and so now the next thing, after I've done the parentheses, I go from left to right doing the ands. So now I do the and. So it's this 1 and that 1 for the whole parenthesis. So do 1 and 1. So 1 and 1 is 1. And I do the 1 and the 0. 1 and 0 is 0. Because they would both have to be true in order to get true. They both have to be 1. And so the other ones here are zeros. By the way, if you do not put the parentheses and you do not label which column is the final answer, I have no way to know what you were thinking. Like, what if you had something what if you had that? No parentheses, no indication which column is the final answer. See, I don't know what you think is the answer. Okay. So there we go. Now that's what you call the closure table. Okay. Now, let's look at the way the questions are worded over here. They say construct the closure table, but then they say something else. You can't just ignore the second sentence. Use the closure table to determine the required conditions for the network to be closed. So they say to do this thing where you determine, and then you look up here in the example and you see how they answered it in the example. They said, they made this English sentence. So you come over here, back to our table, and we just want to say in words, under what conditions is the circuit closed? When do you have a 1 for your final answer? And it's only here at the top row. The whole circuit's just closed when P and Q are both closed. Okay. So that's the problem. Now, let me show you another closure table. I'm just going to show you a student's paper and cover up the name. Okay, so I stuck in the parentheses for them. They left out the parentheses, but they did highlight their final answer, so then that let me know what they were thinking. And so they got their list of 1s and 0s. And now we want to look at that and figure out, how can I say, when is it closed? But I don't want just a big list of bullet points. I want to boil it down to something simple. Well, I can also kind of look at the logic up here. You see, if Q's closed, this one's going to work. If you have Q here, this one works. And this one over here also. as though those are ors. So, so what do you come up with? See, if Q is closed, see if Q is 1, this thing's a 1. So far it's just whenever Q is closed, so is the whole thing. But then you get this one more extra 1 down here at the bottom. So it's closed whenever Q is closed, or this one down here on the bottom where they're all open. See, and now you've got it down to the sentence that you could write for a person, you know, who understands English. Who might not understand that whole darn complicated thing up at the top. Okay. So aside from being worried that this could be hard, I want to see if you're clear on what we're trying to do. Because that's almost, I think that's kind of like the point here, is to understand the goal of logic. I'm looking over here for the comments. Anyone just want to say something? Okay. All right, well, so now you're worried, how would I think of a simple way to say things? So let's see. You know, when you learned algebra, you can take a complicated algebraic expression, you can simplify, you can factor, you can combine like terms, you can use the associative and commutative properties, and you can take a complicated equation with many terms and you boil it down, and at the bottom all it's really saying is x equals 7, right? Okay. Well, wouldn't it be nice if you could do the same thing for logical propositions, logical statements, instead of numbers? I got another analogy. Now, forget about math stuff. There's this linguist named Noam Chomsky in the 70s wrote up models for how language works. He wasn't interested in any one specific language. He wanted to try to find things in common among all languages. And they have systems of rules for taking a sentence, and you can take a sentence and then transform it into the past tense. Or you can take a statement and transform it into a question. Transformational grammar, where you have fairly mechanical rules within a language for doing these conversions. Going all the way back to the first page of the chapter, you know, Leibniz had this kind of a dream. He was like, wouldn't it be nice if we had sort of rules of grammar where you could just change the form of a logical statement, and if the first one was true, then the second one is also true. You could simplify and make new logical statements that carry the same meaning. So wouldn't it be nice where he said it in kind of a naive way. He didn't quite achieve his goal. He had a bigger goal. It was like, could we make a grammar where it's impossible to say anything false? That's the way he put it. But we didn't quite get there. But we did get where if you start with a true statement, you can make another one that's not so complicated. Okay. Well, in regular algebra, what are the rules you have to work with to simplify an expression? Associative, commutative, distributive. A couple of others, some laws of exponents, a few things. The rules in logic, it's the same rules, associative, commutative, distributive rules. I mean, I would not have expected that. Adding numbers and doing ors doesn't immediately seem like the same thing to me. But it is. So let me go back to this closure table and show you how I could reach the simple English statement without having to look at the ones and zeros and without having to think about it very much. The book did not expect that you would do this. They figured you'd look at the ones and zeros to show you what the goal is, what we're trying to accomplish with the simplified expression. We have a distributive property. It's like if I had 3 times 4 plus 5, I'd do 3 times 4 plus 3 times 5. Or I could do. It's not that I would, but it's an option. I'm going to do that here. So yeah, I almost made it upside down there. Yeah, okay. Why am I using the 3-bar equal? It's more equal than just an equal. It's because it doesn't matter whether P and Q are true or false. You can plug in any values for the variables, doesn't matter. The expressions have the same value regardless. This and this are going to have the same value for all combinations of true and false. So, I did my distributive property. Now look at that first one. When is it the case that you have P and not P? Both. It's raining and it's not raining. That doesn't happen. So that first piece is always false. Now, that little wedgy thing there is an R, or, O-R. So we got false, or this other thing. Okay? So that's only true if this other thing is true. See, false or anything equals anything. is like 0 plus whatever. Equals whatever. So the whole expression boiled down to just P and Q. Network's closed when P and Q are both closed. So, you know, if you said anything true, of course you got the credit. But for making the comments, I could figure out whether or not you said it in the simplest way. That's not because I'm good, you know, with words. I'm not. It's I didn't have to think about it. I just kind of did the algebra, and then I could tell, okay, you know, I could write a comment like, yes, this is true, but you could say it simpler. And we're not going to go any deeper. I'm not going to make you solve equations. But the thing to know is there's methods for not just doing the algebra, you know, because the problem with the algebra is, and you have this with numbers as well, you've got choices. There's more than one thing that you could do. And so then there's the whole strategy business. That's why I don't want to go deeper, because it take a long time. But for the strategy, there's methods called Carnot maps, and people who design circuits and so forth learn these things. Well, and there's systems that can do algebra, you know, software systems that will do algebra for you, solve your equations, whether they're numerical equations or logical equations, and boil them down to a simpler form. So, you know, just what you want to be aware of is that what we think of as like human reasoning, it's the creative aspect is we haven't figured that out yet, but how to program that. But the reasoning itself is just mechanical. You know, but all the discoveries in math, they start with this kind of inductive, there's a kind of a creative thing of seeing a pattern where none was obvious, and you know, math, well, the math that gets to be famous, the kind that I admire when I read it, when I see other people have done these things, it's all got a creative angle to it. It's not just deduction. So. Okay. How are we up to here? Anyway, this is one of those rare occasions where if you want to redo this thing, you fill in the words if you left the words out. There's 2 sentences in the assignment. You make the closure table and then you use the closure table. Anyway, you can redo it. As long as you get it in before the closing date, I'll regrade it. Anything else? Okay. So let's see, did you have questions that you wanted to ask from the 3.3 homework? You want me to do a particular problem? Anybody? Going once, going twice. Okay. So then there's section 3.4 in the workbook. Not in the workbook, in the textbook. Well, we did the conditional started talking about the conditional last time, the if-then. We did the equivalent forms of the conditional. The author's got a video on the inverse, the converse, and the contrapositive, these statements related to the conditional. And I want to make sure you noticed the videos and materials that we've got. Let me go over here. So I put up 3 videos from online. You know, this instructor has done a pretty good job with explaining it. So I don't want to just repeat the videos that are posted or the author's video, but I want to make sure you get a chance to ask questions. So anybody on these 3 definitions, so to make the converse, like if it rains, then it pours. Converse would be if it pours, then it rains. We're clear on the converse. You don't change the statements, you just reverse the arrow. And then the inverse, it negates both of them. That's a different meaning, right? When you take a statement, you make its converse, it's 2 different statements. They don't have the same meaning. They don't have the same truth table. Okay. The same way with inverse. If you negate the P and you also negate the Q, it's a new statement. It's not the same. But then when you make the contrapositive, this interesting thing happens. The original statement is true if and only if the contrapositive is true. That's when you make the inverse of the converse. Then you get a statement that has the same truth table like the original statement. So you can just replace one with the other. It's the same meaning. For writing proofs, that's sometimes extremely helpful. You can either start with P and try to prove that, okay, Q is true whenever P is, or you could start with not Q and try to prove, okay, that makes not P. You look at which, you look at the P, you look at the not Q, you say, which one gives me more information that's easier to work with? And that's the one I want to use. I just prove one of these and I get them both for free because the contrapositive and the original statement have the same truth. So let's see. So I made several points there. One was contrapositive is the same as the original statement as far as its truth value is concerned. They are equivalent statements. You guys, you can put that away in your notes or something. So that's a thing to know. And then sometimes it's easier to think using one or the other. You can reason better using one or the other, depending on whether the P or the not Q, which one's giving you more to work with. Okay. Are we good on those statements? Okay. So we got this example. If I get the job, then I'll rent the apartment. The converse is if I rent the apartment, then I'll get the job. And the inverse is if I don't get the job, then I don't rent the apartment. Counterpositive is reverse the arrow and make them both knots. If I don't rent the apartment, then I did not get the job. So the only way to make that natural and flow for yourself is to just do a bunch of them. And so it's this sort of the transformational grammar in English matches up with the transformations of logical statements. How are we up to here? Okay. So determining whether these things are equivalent, well, you'll find out, the statement and its converse are not, the statement and its inverse are not. You just compare the original statement, okay, and here is its converse, and you can see they're just not saying the same thing. See, this one is true. If a statement ends with 5, then the number is divisible by 5, Numbers like 25, 35, 45, they're all divisible by 5. But the second statement's false. You can have a number that's divisible by 5, but does not end in a 5. Those are numbers like 10, 20, 30. So the one's true, the other's false. They don't carry the same meaning at all. So they're asking you to determine that just by thinking about the meaning. But you can also determine it because now you know that the converse and the inverse are not always going to give the same value. It depends on the truth. The truth table is not identical. Some rows might match, not all. Okay. So that I'd be getting ahead of ourselves there. So let's see, on the schedule for Friday, you've got an excursion on something. You get excursion on logic gates in 3.3. Okay. So I just want to draw a little picture on the document camera here. Okay, so if you look over here on the textbook, it's got this mysterious input stream 1100, so forth. And I just want to make sure Just draw a little picture of what's happening with the electronics of it. I think it makes it more concrete. Like that, 1010. It's this pulse. Or these pulses on a wire. You got 5 volts, and then you've got, hey, you got 5 volts, and then 0 volts, and then 5 volts, and then 0 volts. That's the voltage between this wire and the ground. And it just propagates along the wire at the speed of light. You have this other signal coming along, and the clock's real good, so they stay lined up in time. So this digit and this digit arrive at their destination at the same moment. So it runs down the wire, and then it comes into this little AND gate, operational amplifier they call it. And a new pulse comes out the other side that's done the AND. It did 0 and 0, and it got a 0. So a 0 came out first, and then it did a 0 and a 1, and a 0 came out, and so forth. And the only time a 1 ever comes out is when it's 5 volts pulse on both of the streams. And so, well, you can see how it works. You got these 2 streams coming along at the speed of light, and you can just do a whole ton of logic real fast. And so you get how it works. Did we have questions? I mean, I don't know a lot of the electronics or physics about how the transistor works. It's a transistor device, and no, okay. So then they just have these questions where you figure out what comes out. So when it's an AND, you have the flat edge here, and when it's an OR, you have the curved edge, and a NOT is this little triangle thing here. So you've got an inverter and an OR gate and an AND gate. And so you got a couple of questions where you just have to figure out what comes out. And then you've got, you got to design one. Yeah, well. Fortunately, it's just 4 digits, two inputs and 1 output and 4 digits. But you might have to chain 2 things together, something like this. Okay. It might help if you made a truth table or not. You can kind of go bit by bit and figure out. It's hard. Okay. So there's just the 2 questions. Question 1 is much easier than question 2. Well, have a go at it. I want to see how you guys do it. It may be okay. Tell you what, let's treat question 2 as a bonus, but go for those points, get some extra points. And by making it a bonus, maybe I'm overdoing it. I don't want to make you scared by making it a bonus. It's not that bad. All right. So I'll put that in the video here. That way, if I forget, you can hold me to it. Okay. I'm just going to go back to the agenda. I think that's all I had scheduled to talk about. So I mentioned the test, yeah. So I'm going to stop the recording, see if any of you guys have anything you want to ask about.